Hi. So as usual that we start with reviewing what we have done. I noticed last class on Wednesday, right? Wednesday, we have some of you think that I go a little bit fast, so I add more application. In the review, I just go over their slides again, but so I just add them to your new slides, okay? So random variable, okay? So this topic, right, is indeed one of the milestones in this class. If you go to statistics department in the first course of statistics, usually ends here. The reason why, because this is very useful tools of what we call probability modeling, is trying to learn how to quantify your future. If you are focused on random variable, and there's a convenient way to describe it, right? The binomial, Poisson, hypergeometric, and many others. So let's briefly review what we're doing. And in topic 2, we discuss probability, right? We understand how the probability rule works. And topic 1, we talk about data, right? Data with mean and variance. And this topic, random variable, actually combine the two things together, right? Because of, remember, we learned the probability modeling, there's some distribution, right? And based on this assumption, we can know, we can quantify the future. We can make educated guess of what it might be, right? I mean, of course, we give more example, and then hopefully that will relieve your concern. And we also, and how to understand, estimate this model. We don't talk about those, but the data actually help us, right? If, for example, the mean of the data actually can fit into the parameter of your model, okay? And say, for example, the lambda in the Poisson, right? You can learn that from historical data, right? With the mean arrival rate, then that would be applying into this one, okay? So that would be the idea, okay? So let us very briefly go over again the random variable, okay? Random variable again is you put numbers into outcome of a random experiment, okay? And the reason of doing so, there are two reasons, at least. One is to make our sample space more manageable, right? Imagine the stock market, 1,000 stocks, right? So it's very difficult to track this. Then that's why a lot of time we look at the stock market index, like Hang Seng Index, Dow Jones, right? S&P 500, you have look at single number, right? A summary statistics, right? And that would be something we care. We measure the real world, right? So that is the idea. Look at numbers. And secondly, numbers we know how to handle. And as you saw on Wednesday, and you see we can describe things easily, binomial, hypergeometric, all these are very convenient way to do things. Okay. So one technical aspect of random variable is you have to distinguish what we call discrete and continuous. The reason of this is very technical. The idea is simply because of discrete, usually we call integer, right? Usually how integer is 1, 2, 3, 4, 5. And continuous, later we'll learn today as well, is for decimal numbers like price, money, temperature, right? And there's a math that you learn from the high school or elementary school, only apply to discrete. And when you talk about decimal number, it's a continuous, right? Because for any decimal numbers, you can always find the middle one. There's many, many of them. And there's a technical detail how to do it, which require calculus. And those who don't remember calculus, calculus is the thing that Isaac Newton, the apple hit his head and he discovered gravity. Know the guy? Newton, right? Newton. So that's the guy. So that he invent, I mean, together with Leibniz and others, then they invent calculus and they know how to handle this kind of problem, right? And I was like, as you might recall, this related to axiom 3 of our probability, right? They say many outcome, there's many outcome add together, everything still whole. That is the one of the reason why things have become more technical. But we're not stat class, so it's fine. Just I mentioned discrete and continuous. Just to very briefly go over this example again, as a way to remember, is you toss a coin, and it's either head or tail, and they are not number, right? This is a thing called head or tail, and to make it manageable, we know number 1, 2, 3, or 0, and we would delook head is 1, tail is 0. Of course, you can use other numbers. The reason why we use this number because it's meaningful. It's called number of head. Okay, as long as there's a meaningful way to describe your outcomes in the random experiment, that's fine. Okay, there's no limitation what you do, but this is a very natural way to do it. Okay, it's not the only way, as I want to emphasize. Okay, you can put head is 1, tail is -1. What's the case? Maybe you're betting your money, right? If you have head, you get $1. You have tail, get 0, -1. You pay $1. It's also meaningful. That's fine. That's no problem. As long as the assignment is meaningful, it's okay. But we will usually use the way that is useful, right? That's how you put numbers, associate each outcome with a number in the what we call the support of the random variable. Okay, this is the sample space, the right-hand side support, right? This is called the diagram, functional map, and you can do this for two consecutive toes of the coin, and there will be 4 outcomes. But if you just record the number of heads, okay, in that case you don't care about the order. It becomes 0, 1, and 2. It's substantially reduced. You can imagine if you toss a coin 10 times, then the sample space is more like 1,000. But the number of numbers that you can assign, number of integers you can assign, just 0 to 10. So just 11 number. That makes our life easier. Okay. Of course, by making the number of the numbers you can use easier, you have to describe the probability in a more complicated sense, right? Because if you have thousands outcome, each outcome is equally likely. But now you have only 11 outcome, suppose toss coin 10 times, right? Then your thing become look like a bell, right? So you need to write to describe the bell thing. So by making something easier, you make something more difficult, right? So that's why we need to learn the P, big P, and also the big F, right? The distribution function and the cumulative distribution function. So that is the idea. Remember, continuous is the money or temperature, or usually it's a real number, or what we call the decimal numbers, right? So just to very briefly say the px, right? It's very simple, right? Because the value you can assign to the outcomes are just, you can count it, 1, 2, 3, 4, 5, right? So very naturally, the thing you want to describe this random variable, right, is to tell me this number was the probability, right? Remember, this is trying to tell us how you describe this random variable, because now we don't have no longer event. Every event is represented, or outcome represented by number, right? So you want to see this number will realize how likely this number you will see, right? This is what it is. There's nothing special here. Okay, I think I'm not going to go to this, but the idea, right, is like 0 and 1, and each one is 1/2, right? And this one is the equivalent way as P. It's just adding up the things less than or equal to a number, okay? And the idea is if the table, right, you just go up and left, right? The F is obtained by go up and add everything on the left-hand side, right? Say go up and add everything, right? So there's nothing, this is just by definition F, right? And graphically, right, the P is the bar chart. Actually, I think everyone would understand this, right? But F will be just stacking, right, up the stuff, okay? And this intuition carry to continuous, as we have talked at the end of the Wednesday. So that would be the idea behind, okay? So I'm not going to go into detail, But I do have to point out clearly that one of the good things about you convert things to number is each number is mutually exclusive, right? The random variable equal to 3 and 4 cannot be equal to them at the same time, right? So that's why a lot of things become easier because mutually exclusive, right? Adding event and they cannot happen at the same time, right? They're mutually exclusive, right? And you can just add them, right? And the same, right? How you change from big P to big F, right? It is basically stacking, right? And I hope some of you would play Legos and wooden puzzles, right? If you are able to come from the left to the right, you should be able to see how from right to left. It shouldn't be difficult for you to see how you go from right to left, right? Say, suppose you subtract these two columns, give you this one, right? So actually P and F are the equivalent way to describe. Why I say that? Because later you will see usually when we define continuous random variable, we would tend to use F, okay, instead of the P equivalent, okay, because this is more natural in continuous. This is more natural in discrete, okay. So that's why we have to talk about both, right? Otherwise, why bother, right? Why don't? Because P is sufficient for most purpose. And the reason why I talk about this is not because the book talk about that, right? But because of to understand continuous, this is the way to go. Okay. So 1 to 6, I'm not going to talk about that. You should know it. So the expectation, just to remind you this very important concept of expectation, is actually related to what we learned topic 1. We call the most important summary statistics we learn is mean, right? Mean is just the average value, right? It's just adding up all the observation over the number of observation. It's a fraction, right? And here is the same idea, right? We also have a number, right? Number from what? Number from random experiment. And suppose you run this experiment many, many times. Every time you convert to a number, right? You have a bunch of numbers. And average of this number is expected value. Okay? And the formula is like this, right? You just multiply, is a weighted sum, is x multiplied by the probability, or is actually weighted FH, but are the same idea, right? And the proof is already set here. I mean, of course, you can make it general, but this is the idea. Just repeat, right? If you have toast a fair corn 1 million times, or even more, if your corn is fair, you should expect half of them are head, half of the tail, roughly, right? And you expect 500,000 0 and 500,000 1, right? If the random variable is number of heads, right? If your tail is 0, your head is 1, right? So 500,000 0 and 500,000 1. And average of this number, right, will be you add up 500,000 1 and 500,000 0 over 1 million, which is 1/2. Same as the idea if you 0 times 1/2 plus 1 times 1/2, right? So this is exactly what it means, and you will be seeing this. Okay, I'm pretty sure this class or this topic is more mathematical, but this is actually the main thing you want to learn from this class is the probability modeling, how to model probability, right? Because there's something probably you don't learn it in your high school, but this is the thing. I mean, you learn, of course, you learn mean, you learn probability, but how to use this probability to quantify the future is the thing we learn this class. So that's some new thing to learn. And I also, to reduce the anxiety, I also put up the homework 2 on the blackboard. Of course, you always have 2 weeks to finish your homework. So I put up there, and you can see what kind of homework we're expecting you to do. But it's no different from the example, the green box like this. Okay, so make sure that if you do revision, make sure you understand the green thing, also the purple thing, right? The purple box. The black box you can safely skip it. Is also fine. Okay, it's good to know, but doesn't really matter. But also, of course, everything in the homework will be the thing that I care, right? And you expect the same thing or similar thing, of course, in different angle will be asked in the test. Okay, and do remember there's a lot of formula though, but we are not asking to memorize, right? You can bring the hard copy of your notes. You can make infinite number of cheat sheets. That's no problem. Okay, as long as you don't share with your classmate, you can bring as many as you want. Okay, and okay, so that should be an issue there. Yeah, I don't have a problem here. Next is expectation and variance. Okay, and same expectation I've said, right? And expectation is the thing you care, especially when we thought about application in finance, right? We care about how is the return of our investment, which is a future thing. We care about average return. It is something we expect our return to be, right? And this formula tells you, right, some property of calculating this is my portfolio has A units, A share of stock X, and I plus some cash on my hand. What is my expectation of portfolio? It's easy because of the linear property of expectation. You just care about the expected value of the stock, okay, and times A plus B. So it makes our calculation easier. Okay, so that is the idea behind. Okay, I think I add this particular slide, just like this. I mean, there's nothing new here, right? So the stock can have 3 different prices, 1, 2, and 3, with different probability, and you can calculate expected value, right? It's 2, it's symmetric, actually center at 2, right? And imagine that you invest 100 shares of X and have $300 in my hand, don't invest. What is the portfolio expected, right? So you just calculate this way, okay? I put it there because just to make it to see how to do it. But there's nothing new here. I mean, if you have old version of Snook, it's fine. Okay? Because I add them because to make it easier. So variance is the same idea, right? You just do this experiment many times, right? You had numbers and you can calculate the variance. Do remember that variance looking at how spread out the data is, right? The more spread out, then this is bigger, right? That's the idea. And the exact definition is called this average square distance, right? Look at the distance from the mean and squared, right? So that's the idea, right? So we learned that in topic 1, and the calculation is following this, right? Every time you take a number, look at the value of 1, you minus the mean and square and times probability, and they do it for the rest. Okay, and you're the same the variance of this formula, and if you do investment this way, you care because variance is what we call the risk, right? And the risk is how variation, and you don't like variation, right? Because human by nature usually don't like, in terms of investment, don't like risk. You go to finance class, this is the risk measure, right? And it's saying that the portfolio, the risk of portfolio is independent of cash because cash is no variation. And if you invest 1,000 stock, 1,000 shares of X, then your variance actually will become 1,000 square. Okay, but do note that the SD, the standard deviation, is just multiplied by the number of shares you invest. The reason why square because variance takes square, and you if depend on whether you want to use variance or standard deviation as a measure. Okay, also risk. Okay, and this is trying to show you how you calculate variance and how you can convert it to your risk. Okay, and there's nothing new here, just applying that. I add them because some of you said in the new reply, right, that I want to go slower and see more examples. I just add them. Okay, but there's nothing new from what we learned. Okay, and this bivariate I'm not going to review. Okay, so quickly, just to review what we have learned here because they're so important, and I want to take a very brief review on that. And they are important because it is by themselves is already useful. Okay, and the reason why they're useful is this because probability is a language to describe the future, right? And this is useful for business decision, right? Because always look at the future, right? And there are 5 types we learn, right? And probably the second one is the baseline, so we don't really worry, but basically there are only 4, right? Because Brignoni is a special case of binomial when n go to 1, right? So that is there are only 4 of them. And let's go to uniform. Let's go one by one, right? Very easier to think, right? Uniform simply means all outcomes are equally likely, and it's not directly useful, okay, in most cases. But if later when you learn, when you try to learn Bayes theorem, right, you apply Bayes theorem to this, and then you keep learning, and then you get the real thing, right? You always start with something uniform. If you don't know what's going on, and your data comes in, you update. Okay, the Bayes rule with uniform will be real powerful too, but we don't have time to. I mean, this is out of the scope of this class, of course. I mean, if you want to learn this, it will be like 4,000 class, advanced class. Okay, but this is something that will be useful, and it's still useful because uniform is something we have no idea what's going on. Then uniform is the best thing. Okay, because you don't want to bias your calculation. Uniform would be the best thing to do if you don't have idea which one is more likely. Still is a useful one. Brignoni, to repeat, it's just very simple idea. You just make the sample space is either 0 or 1, right? It's either success or failure. You just say, decide, look at the future. You just have 2 choice, success or failure, right? And success is correlated P, and failure is 1 minus P. And of course, for those of you who are math inclined would think, okay, why stop at 2? Why can't I 3, 4, 5, 6? That's fine. That's definitely doable. And there's something we call multinomial, but it's not within our syllabus. Okay, you can study them in a more advanced class, but it's doable if you have more than success and failure, right? We may think about how to go to school, right? I go to school by bus, I go to school by train, I go to school by walk, right? Then it's more than 1, more than 2 outcomes, right? But we just focus on the case where you go to school by bus or not by bus. Okay, I forgot the train or walk or drive, right? That's a different thing. Okay, so just 2 binary outcome, okay, for our class, and this is already useful for most of the purpose, I would say, unless you're doing experiment. But for business decision, I think that is enough. And for you to learn the new distribution, right? The things is you understand what is the usage of this, right? And how it looks like the polyfunction, what is the mean and variance, right? This is the basic understanding you need to know, right? And P, expectation and variance, is right the summary statistics, right? What you expect. If you model what you want to model the future like this, what you expect and how variation they are, right? Same as the idea, right? Because you try to summarize, right, your future, right? Then you give the mean, right? How accurate your future is, the variance, right? So that's exactly what you learn from the thing, right? But the idea is how do you get the P, right? It's from data, right? You know historical data, right? And from data, you learn the P, right? Help you to guess the P and use this idea to predict the future, right? That's you learn from the past and future. In the middle, you have the assumption of the modeling, and you can assume the future looks like binomial. So Brignoni, that's fine. Okay, so that's the idea. And you can also generalize this, right? Instead of thinking about the future is Brignoni, the future is more general, it's a binomial. Okay, just to give you a figurative idea what is binomial, is the idea the following. Okay, we have box. Okay, Brignoni is saying that, okay, there are 2 possible outcomes, right? Either you are success or you are failure, or maybe you are failure, right? Success for the P and 1 minus P, right? So this is the Brignoni, right? If you think the future is only success or failure, this is try to see, right? Whether you can do business tomorrow or whether stock price is going up or down, right? Today or not, right? Is P, right? That's how you model the future, right? And probably you would think, okay, it's more fun to think about more boxes, okay, and each box will do the same, right? And the outcome of the first box doesn't affect the second one, and so on and so forth. That's independent. If that's the case, if you have n box, that your future can be described as binomial. If you only care about the number of happiness and number of sad, right? You don't care about the order, right? In that case, you can model the future as a binomial, right? So this is the idea, okay? And I'm not going to explain this formula, right? This formula is usually you use Excel spreadsheet to calculate, it's already there, but I give you the idea why this is true, okay? And what you learn is you summarize it with NP and the variance like this, right? NP times 1 minus P. I'm not going to explain this one. Rather, I focus my time on the example again because this is why we need them, right? Because suppose you are going to say, this is what we call the example of inventory management, right? You imagine your shop owner, you need to see how many customers like spicy food. The reason is because you need to think how many food I need to pickle, how I have to put there, be prepared before the client comes, and you to see how much portion to prepare, right? And if 30% is coming, right? P is 0.3, and suppose you expect 5 customers to come, right? How much food you need to prepare? Of course, the most direct answer would be you may prepare the mean, right? Which is 1.5. But mean just simply mean you will hit half, you will be enough of 50% of time, you will not in 50% of time, right? Because means in the middle, right? So that's why sometimes you need to go back and look at the probability, right? And we look at, okay, how likely that 2 people would come, 1 people will come, 0, or up to 5 people will come. You can calculate this probability, right? So I plug in the formula. And the important part is you can calculate the probability less than or equal to 2. Why? Because look at this number means no more than 2 is actually 84%, right? If for you think 80% is safe number, then this is your decision, okay? You tell me your threshold, then I can tell you how many to prepare, right? Of course, if you want to be 100% sure, of course, go to 5, right? But always this is going to be wasteful. And what is the optimal decision? It depends on cost benefit function, right? What is the losses to your, you can define losses if you're unable to serve customer, right? And then based on that, you can do an optimization problem, okay? But here we don't define how you think about the losses and gain, but even with this, we can still do what we do, right? Use the probability as fractional, but you can do more, okay? Is that clear why we do this? And probably I add this technical slide as well to give you idea what are the example, because as I said, this is one of the big milestone of this class is to learn how to use probability to describe your future uncertainty and the application. I'm not going to each one, but at least I go to 2 of them, okay? The first one is you consider the marketing. I will go to the more detailed one, okay? Maybe this one, okay? This is just simply go to the first point, okay? Assess the probability of marketing campaign by calculating probability of achieving number of purchase, okay? The idea is following. Suppose you're going to send a leaflet, okay? And you're going to print out 10,000 leaflets and send it, say, outside the subway station, okay? And you guess that the probability that a person who pick up your leaflet, 5% people are going to do it, okay? And this one, you can safely imagine this open-end box, right? Because this is similar to the idea that, right? You are sending to leaflet to each one is open-end box, right? It's either success or failure. Okay, that's how you understand the binomial, right? Because it just, each one is a box, right? Send it to him whether he'll buy or not buy, right? And you can imagine that they're independent if you assume this is the right way to do it. And this is a binomial. And you can calculate any probability that exactly 500, right? You can calculate any number by doing this formula. And by having this formula, right, then you can evaluate your success, right? Because at the end, you can calculate how many people come with the leaflet, right? And then you can see how successful the campaign is, and then you can decide whether you want to do it or not, right? Because this 5% is estimate, right? You want to actually come up with the right number, right? Or whether this time, even this is right, I want to actually say how much stock I need to prepare for my shop, right? So this, a lot of things can be done here, right? But this, how to further use this information will be beyond the scope of this class. You learn it in other contexts, right? Because the application, how to use this probability, it depends on what's the usage, right? But by quantifying under this process, you know the probability, what outcome when realized, and you can make decision, right? Depending on the use case. Is that clear why we do that? Okay, give them one more example. Okay. For example, you're doing quality control, right? And you want to decide, okay, how many defective numbers from your production bench. Why you want to care about that? Because say, suppose you have to handle the defective stuff, right? You want to put it in the recycle bin, or you want to check things out, right? And what you're going to do is you could get a sample of 100, and you know from historical data, 2% of the product is going to be defective, okay? And you want to calculate probability exactly 5 outcome is defective, and you give this probability, right? And the reason why I want to calculate this, right, is because you want to see whether this defective rate is the right thing, right? Because you're supposed auditor, right? You want to check out whether the defect rate is right, right? If not right, then probably there may be some internal control problem within the firm, right? And you know the probability what may realize, right? You can look at what you actually observe and compare what in theory the probability give you, and you can decide whether it's right or not. Okay, this idea is hypothesis testing. We'll touch this in 2 topics later. Okay, but this is the idea. Okay, this is the idea. Okay, I'm not going to go to every single detail if you can check it out, but you can see the idea. Again, the binomial is coming from this concept. Okay, you can imagine the n box. You open each box. The outcome of each box only you can classify success and failure. Okay, and each box is independent and identical, okay, the same way. Okay, so if you think the future this best describe your situation, then you can use binomial. Okay, is that okay? And for the Poisson, will be the same thing, right? Why the Poisson is the same thing? Poisson is simply that I open the box, but I open many box. Okay, and why is opening many box is like this, right? Because Poisson is simply said this idea is this n go to infinity. Okay, and why n go to infinity would make sense? Because Poisson actually do the following. Imagine this is the timeline. Okay, maybe an hour of timeline. Okay, 1 hour. Okay, and 1 hour we can divide this into 60 interval, right? And each interval is 1 minute. Okay, and you can think, of course, you can even cut further to 1 second, right? Each minute can cut to 1 second, cut to as small as you can think. And you can imagine each interval is a small box you can open. Okay, and you can imagine that only open you have yes and no, right? And yes means someone arrived. Okay? Someone come. Okay, the example would be you can think of cases your restaurant, You think how many people would come in the door, right? Success is someone come in, failure is no, right? And this is how many people would come in, right? If you add them up all, okay? And for Poisson, is N is very big and P is small. P is small, okay? And P is small is very natural. The reason is because you cut this box so small, right? The probability that actually someone come in at this small incident is very small, right? So that means that that is the Poisson, right? Is to the use case, as you can see, is you want to have a time period. You want to see how many people is coming in, right? Number of customers arrive within a given period, right? So do note that when we model Poisson, it's much easier because we need only to know the lambda parameter, right? The lambda, because we define MP is lambda, right? Which is the average number of people here, right? Lambda turns out to be the mean, right? So if you look at this, is on average how many people actually come in is the lambda, right? And this is how you model Poisson, right? And I give example again to see, to give you more idea how we do that, right? And this is the formula, right? And do note that mean and variance the same, okay? So the idea is like this, right? Suppose a restaurant, a customer coming for the Poisson, we probably mean 5, right? So we just apply this formula. You can calculate exactly 2, okay? And of course, you can calculate exactly 1, exactly 0, because you know how to describe that, okay? And why we need that? Because this helps us to quantify the future, right? If you think about your data like this, you can do decision, right? Say, suppose you can decide how many workers you need to have, right? And how many food you need to prepare, all right? And there are many applications, right? For example, if you're a call center, you can decide how many people will call in and decide how many staff you need to deploy. Or website traffic, you can decide within this time period how many people will come in, and you can decide how big is your server, what is the bandwidth you need to buy, all right? So example like this, I just do the call center case, right? On average, it's 50 calls per hour. How to do that is historical data, right? And you can imagine that this is a following Poisson, it's naturally, right? Within a period of time. If you think over 1 hour, okay, is each second is like a small box, right? Whether some people call in this second should be independent of the call in next second. If you think this assumption is right, Poisson is the way to go. And then you can calculate exactly 60 is this number. You can calculate the probability, any number, right? And then further you can do decision, okay? How to do it further depend on use case, and you will be studying in more advanced classes. When you do 3,000, 4,000 classes, you will learn that. But you know how to describe the future because this already tells you the full description of the future, all right? Because if you use the data, right? Remember, what you do is very simple, right? This is how you predict the future. It's very simple. We just need this. We just need historical data is 50, right? And then by making assumption on Poisson, we know the future. At least I have an educated guess of the future, okay? And that is the power of the model, right? As long as we accept the assumption that within an hour, every minute is independent, right? Whether people call in the first minute will be dependent of people call in the second minute or so on and so forth. Well, each minute is independent of each other. Poisson is the way to model, okay? So that is very simple, right? Because you can see this is very powerful tools. How do you further use it? As I said, is in the other, will be depend on your application in the future. Same is like this, right? Website traffic, right? You base on the data, 500 people come in, and you can assume a Poisson, right? You can tell how big should your server should be, right? And you can decide what is the maximum capacity of server to make sure that it doesn't break down, right? So that how to make decision, of course, is beyond the scope of our class, but that you can see it can be very useful. Lastly is hypergeometric. Okay, I just want to remind you this by graph, because this is the thing is most easy to understand, right? Is you can imagine the you are in fact not open a box, but you are having a you have a big N. We're supposed to have 100 of stuff there. You go to warehouse, you go to the check the inventory, right? And you were told that 30 of them are actually good. Okay. Okay. And out of that, you have 70% are bad. Okay. And this is the data given. Okay. So you can see it's much more. We need to know exactly what you have in the sample. Okay. And that is usually good because you go to audit, right? You know how much stuff in the warehouse. You know from the client tell you how many are good, how many bad, right? The thing is to verify. Okay. So you go to audit, then you would do what you do is, right, you would just go to pick up some sample over here, right? Maybe I draw in this way, it's better, right? You will draw N, maybe you just draw 10 item out, right? And the question is, X of them will be happy, right? And N minus X of them will be sad, right? And depend on luck, right? X can be a number from 0 to 10, right? So hypergeometric is asking what's the probability of different value of X, right? What's probability of 0 up to 10, right? That's the idea, okay? And this is what we do, right? This is we do some sampling over there, right? So it's all quality control audit is actually every time you do. Is that clear? Okay. And here you can imagine highly related to what we call sample with replacement or sample without replacement. Okay. Because we take 10 people and we take this means that we take it out and we don't replace, right? We don't put it back, right? So that's why each take is different. So that's why hypergeometric. If you take some out, put it back, then is binomial is better, right? So that's why when you can imagine that when N is super big, compare your small n, right? Whether you put it back doesn't make a difference, right? So then binomial is the same. So you can actually see all the result is when the big N is compared to small n is big enough, everything actually very similar to binomial. Okay. And that's actually what you do if you have super big N, right? You have super big warehouse, you only get 1 or 2 items there, right? Or 5 items there, then binomial is fine. It's a good approximation. You don't have to bother with the hypergeometric. And actually you can see this from the formula, right? And if you look at the formula, if N, the big N is super big compared to small n, then actually everything boils down to binomial, because A over N is P, success, right? And N minus over N is 1 minus P. So everything actually go back to that one. Okay. So I'm not, I think it's fine. I think that's now the example. I just go over one example. The reason why I have extended long review of what we have done, because I think, one, this is very important. I want to emphasize it. Second is some of you actually told me that I go too fast. So I just slow down a little bit, just go over again to make sure that the point is being clearly conveyed, because as I said, this is one of the milestones of this class. Okay. If I miss that, then I'm not doing the right job. Okay. Okay. So that's why I apologize a little bit repetitive for very advanced student. Okay. So here I have 100 items. So big N is 100 and 10 is defective. Okay. Do note that the smile and sad face can be depend on scenario. In this case, defective is the happy face, right? Because this thing you care. And you can imagine that here I take the sample of this is small n, right? The question is asking how many defective items, right? It's 3, X is 3, so you can just put the formula there and just apply and ignore the P, right? Because once you know the big N, small n, and A, right, the 3 numbers, right, or called 3 parameters, then we exactly know how you describe the future, right? As long as you told me in the warehouse how many goods you have, how many good items you have, how many bad items you have, you tell me how many samples you want to get, then I'm done. I know exactly what's going on there, right? So, and how to make decision if there's something in the future, depend on the use case, right? But with the probability, you have know everything in the future, right? Okay. Send a question. Because I do extended review, maybe I steal 5 more minutes because I think that would be before the break. I hope it's okay. I still 5 minutes to talk about this. I mean, you still have 15 minutes break, don't worry. But I just want to continue with this one before the break because it's good to cover something new. Okay. So continuous random variable. Okay. So what we actually learned from this, actually everything carry out to continuous with some twist, and the twist is technical, so we don't need to care. Okay. But we need to know conceptually how it is being done. Okay. So if you still recall in discrete, we have big P and big F, right? And big F still correct. There's no problem. The big F is still the probability X less than X. Okay. But how to define this is not clear because it's very tempting to write this. Okay. It's very tempting to write, okay, remember the formula for this guy? It's just summation P of X, right? Sorry. P of Y and Y less than X, right? X is a number, right? So there's time to do that. But the summations are adding things up. It's a problem because infinite sum, right? It's not easy to see. And if the P is well defined, turn out to be not well defined. Okay. So then how can we do about this? Then we don't have to, we can use it, we have to use integration, but that is beyond the scope of class. So we can't really do it. Okay. And do we have something like P? It would be something like F of X, but we will let me use an example to explain how the big P and the small f are related. Okay. Let me use example to motivate this. Okay. How I motivate that is by go back to this example. Okay. This example toss a coin. You toss a coin, 0 and 1 is uniform, right? And how to get F is stacking. Okay. I think we talked about this in the beginning of our class today. Now suppose you have 3 outcomes. Okay. 1, 2, 3. Okay. Uniform again. You have 0, 1, 2. How you get a big F? Again by stacking, right? It's stacking out 0, 1, and 2, right? You can imagine you repeat this thing, right? You can have 4, 5, or 6, or 7, okay, and so on and so forth. Okay, so this would be 1 or 2. So you're getting this thing, we're getting smaller and smaller, right? And this is the same, you just get stacking thing up, right? I think you can imagine that, right? You keep going, you can keep going this process. Okay. Means what I mean is you will be drawing more and more thing, right? But this thing will shrink smaller and smaller and smaller, right? Because this must be up to 1, right? The height must be up to 1, right? Getting smaller and smaller, right? And you can imagine you get so small, it becomes 0, right? You can't draw anything, right? But for this one, it's still a well-defined, right? Because this is just stacking things up, right? This thing still looks like this, right? At the end of the day, you possibly get something like still got a line, right? Horizontal line, right? So this is no problem defined. Okay? And this is some problem to define, right? There's still some problem defined. But we know that this guy should be something flat, right? Because you should expect this is something flat. right? So that turned out to be, we can define something called small f, okay? Is similar to this idea, the P, okay? It's just because this is flat, right? We flat out, we just have a line there. And what is the value of this line? Okay, it's coming from the area, right? The idea is same as what we big F and small f is come from 0. Okay, this area, right, stacking out is, suppose this is x, will be this the level of this. Okay, let me draw this out again in a diagram, maybe better. This is no, doesn't look seems to be good enough. So you can imagine we describe f, how f and big F related. We like this. Okay, suppose I have any arbitrary thing here. Okay, I start from A. Okay, A here. Okay, and I start from 0. Okay, and up to B. Okay, and we know A starts from 0, B must be 1, right? There is no doubt. Okay, so how this line being drawn, okay, will be stacking things, right? From left to right, just stacking. Okay, so imagine up to x here, x is here. How we do this is like, look at this bar, right? Blue, right? This blue here, just stack, right? You just keep going this, right? Maybe the way I stack is stack backward, right? So I just do this bar, go from here, the stacking, right? And I have a purple one, I stack here. I have a green one, I stack here. And I have, lastly, I have blue one, I stack here. Okay. So it's just, I stack this thing to become this, right? So that means that the area for the small f, okay, will be the height of big F, right? That's what we learned, right? The area of the P stack up become the big F. Okay. So, and if you learn calculus, that is actually integration. That's why you see the S sign. Okay, but we don't know about calculus. What you need to learn from this, actually, we'll do a break now, is to understand how to relate F and big F. It's simply stacking this means the area, right? Is actually the height. Let me repeat. The area of the small f become the height of big F. Repeat the statement because it's important. The area under F, will convert to the height of the big F. Okay, and that's how you do this. And this area, right, by construction, is saying that this area of height is this area of size is the probability that the x is between A and X. Okay, that's the idea. Okay, this number X, right? The random variable between this area will be the size of the area. Okay, and this is the thing that we'll use the rest of the class. Okay, we will not use this F. Okay, we'll use this directly. Okay, this is the two things you need to understand. Okay, just repeat before the break. Sorry to reiterate because you guys said I'm too fast. Okay, I just repeat the main point here. How to understand the small f and big F. First, area of the F give us the height of the big F. Okay. Remember what the big F is, right? Big F is the probability. This height, right, is actually the probability that x less than or equal to x. Okay. Remember the meaning of F, right? Less than or equal to. Okay. And actually, by this concept, the area between any two number, right, A and X, will be the area in between them. Okay, So that's the idea. Okay, we'll use this for the rest of our course indeed. So don't worry, you must understand. There's no way you don't understand. So this is something we will do. Otherwise, you can't do any assignment. But anyway, I hope it's clear. So let's have a break of 15 minutes. As I promised, we will have 15 minutes break. Okay. And then I already set the U reply. You can tell me how you feel. Okay. In the break. Okay. Let's resume at 10:40. I understand it's difficult. So in the meantime, if you have any question, please ask me. I'm happy to answer any question you might have. I'll go around. Yeah. I will resume at 10:40. Any questions you might have? So I guess time. Let's see. I hope you fill in the form so that I can keep tracks. Binomial and hypergeometric. The only difference of the main difference is binomial, each box you open is independent. Okay, whether the first guy, the second guy will be independent. That is how you use. Hypergeometric is not, because you pick up the first item, you do the audit, then it's removed from that, right? The second one you draw is different. So each drawn is different, right? So it's different in that case. So that's why it's different. Is that clear? Okay, suppose this is how I do the binomial. Suppose I see how many people are happy or sad. I come in, I come from outside us, I grab 10 people, ask them happy or sad. Then it's hypergeometric. If I go out and come in, take up a particular guy, happy or sad, and go out again and come again and do it again multiple times, each time is independent, right? So then it's binomial. Is that clear? I don't know. If not, then let me know. I can try to give you the idea. But anyway, the difference is binomial. Each drawn is independent. Hypergeometric, you just drawn once and for all. Okay? So I hope that is clear. Not yet? No offense. Totally not understand, so no question. If you still have questions, I highly recommend that you talk to TA because our TA is very friendly, and of course he's very busy, so please make your appointment with him so he can explain in more detail. But of course, if he can't solve it, I'm always available, or you can email me. Or because of this class is a record, I hope the record will be good. You can see, but the main thing is if you know how to handle assignment, you'll be fine. Okay. The second thing is actually in the break, some of you ask, how can I distinguish which scenario use what distribution? And that is way beyond the level we are talking. We will give you what distribution, you just do it, okay? To identify when to use what is way beyond introductory class. If you know how to do it, you're already in the master level. Undergraduate, you don't expect this to be happening. Okay, it's very difficult to know which one would fit what. Okay, if you know already, you go to work, right? It's very difficult to do this because once you know which distribution you do, then you already solve the problem, right? So it's not easy. So I have to emphasize that. Yes, it's very challenging, as I said, because this is the most useful thing in our class. One of them, right? The second is regression and ANOVA, second thing, but this is the most important thing. Okay. So that's why it's challenging indeed. As I mentioned already, right? This is usually the end of the first stat class. If you go to stat department, and in old days when I do 210, 210, 2011 in 2 years ago, this is, I spent whole semester for all these 6 weeks. I think this is 5th week, right? The first 5 weeks, right? So we condense it to 5 weeks. Of course, it's difficult, no doubt. I don't want to say it's easy, but I hope that the way we cover is still meaningful. Okay. Most of you are okay. Okay. Okay, that's good. It's windy. I hope the typhoon is not going to affect us. So sample proportion. Well, is it in my class? I've even covered this in it is in next lecture. But anyway. Oh, is it in the same class we are in? Somebody said it's the next class. It's not this class. We haven't even talk about that, but anyway. Yeah, maybe he's looking at some more advanced. We are not talking that yet. Yeah, F and F. Yeah, that's right. So pretty much no one. Okay. Is I hope currently is a little bit okay, but I'm pretty sure that still fast for many of you. But oh, sorry, run out of offensive jokes. Any guess? Let's try. Okay. 3 more seconds. 3, 2, 1. Let's get. Oh, I see. North Point. Okay. Okay. I really appreciate that the one who make the joke, because make our life happier. Okay, I'm going to close it. In case you have anything, then let me know by email, or I hope that so here we have continuous thing, and we also have expectation and variance as we do the discrete version, but we need to do integration. But don't worry, we never use this for calculation. But just to remind you that we can still do calculation in a similar manner to what we do. I'm not going into the definition because it's more calculus, but the idea is the same. Okay, if you know, you just change the summation side to the integration side. But the main idea why we care mean and variance is the following, right? Just remember why we care mean and variance. It's just a stock market idea, right? Expected value is just the mean return, right? And the variance, the risk, right? You will talk about stock price, that is something you care, right? But I don't want to go into much detail on those because we don't use this in our class, but it will be very useful in the future when you study further. Okay, but for class we don't care that much. So for modeling, probability modeling, we will often use the first 3. Okay, uniform, exponential, and normal, which later you will see. Normal is indeed a bell curve. Okay, we'll do it in very great detail because we'll use this for the rest of our class. And uniform is as same as a discrete version, right? Discrete in uniform is like every number is equally likely, and uniform is also the same thing. Also very useful. And exponential, later you will see, is actually closely related to Poisson. Okay, Poisson is asking how many people come in a period of time, right? And Poisson is asking how long it takes for a guy to come. Okay, and you will see they are close related. I mean, actually the same thing. Okay, it's very, very similar. Okay, and the rest of it with chi-square student T and F, we will very briefly go over because they actually a thing that related to bell curve, and this will be useful for the rest of the course. Okay, we don't use it for direct modeling. Okay, but they will be used for our calculation. Okay, but at least today I hope I will go to the bell curve. Okay, and then left the rest of the fee for the and the Excel for the rest of the class. So we hope to finish next week for this. That will conclude our first half of our course, right? Probability modeling, right? So uniform, okay, by construction, it's not very difficult. It's simply saying that two number A and B is bigger than A, right? I said uniform between A and B, right? Just draw a number there, okay? And this big F and small f, you don't need to worry, okay? Usually this is something looks like this, okay? The F is like this, okay? Indicate that each number is equal, so it's a flat one, right? But that is nothing new. If you recall, just generalization of this guy, right? This is just simply flat, right? And this is upward sloping line, so there's nothing new from that, okay? And for those QFN students, although I skip, you should be able to do the integration and see how you do it. I'm pretty sure you forget many integration thing, but you need that, and then you have to do integration by part if you do it in the right way, and that is complicated. Okay, but you will need them if you want to go further. Okay, but this is not our class, so I just need to warn you that this will be needed. But okay, and here will be the idea of the uniform. It shouldn't be difficult to see. Uniform from A to B will be just A plus B over 2, just half in the middle, right? Expect the variance is slightly little bit tricky. Turn out to be is the range B minus A square over 12. The 12 is something a little bit tricky. I don't think I have a good explanation for that, but just integration result. But anyway, this is the one, and I want to be very brief over this because usually you don't use this directly. Okay, but I just telling you put it there because QFN student would be needing this for knowing how to do the variance expected value. So if you're QFN student, please try to prove the variance and expectation. Of course, I have the proof already in the slide, but you can try to understand the proof. That might be useful for your purpose. Okay. I'm not going to say anything about that. Just to see the variance is proportional to the range, right? The range of this is B minus A, right? The data you got, right? The bigger the range, the higher the variance, which is natural. Okay, look like this. So look at the example. I think that's the thing you need. Okay, and do remember, uniform is the way you model when you don't know anything. Okay, suppose the rainfall, I think non-uniform would be a good idea if you don't have a good idea. Unless you're a scientist, you may have a good idea what is going on, but if you don't have anything, that is a good one. And if you think the rainfall is from 1 mm to 4 mm, right? Then calculate the mean and variance because A is 1 and B is 4, then it's plain. Okay, that is the way usually we use for the uniform, right? Okay. And something like what's probably between 1 and 3. Okay, and this I think would be the thing we would be usually you would to do is for continuous, we always want to find the probability between two numbers. Okay, that is a good illustration of how you use it, right? And to do that, right, between 1 and 3, okay, and you would be actually doing what we call the addition rule, right? Between 1 and 3. Okay, you can look at this. It's just simple math, right? Let's draw this F, right? X here. Suppose uniform like this, right? It's 1 and 4, right? 1 and 4, right? This is the F, right? And 1 and 3 is simply what? These areas I mentioned, right? And according to the graph, the height of this is the length, 1 over the length. The height is 1 over B minus A. So it's 1/3, right? So you know the height is 1/3, right? The base is a rectangle, right? The height is 1/3. The base is 2. 2 times 1/3 is 2/3. Okay, so you can use the graph to do calculation, right? Remember why this is just to recall. The graph is like this. Let me raise again, right? The graph is like this. The F uniform from A to B is just A to B, and the height is just 1 over B minus A. So this is the only point. This is the only graph you need to remember, right? This is the thing you do, okay? And this is the formula, the F. You can have the formula actually from here, right? This is you can forget this guy, but this is the thing we need, right? This is the thing we need. Okay. Probably you would probably need this formula in your toolbox, right? This is the thing you need, right? Either one of them will work, right? But we know that it's going to be from that you can do the direct calculation of area. You can get that, right, as I mentioned. Or you can use the big F function. That is usually we do because this is the way for most of calculation. We can't easily find area because for rectangle it's easy, but if other shape you can't really do it. So what you do is we know we use the big F to do the calculation, right? Because the question is asking 1 to 3, right? And I have F here, right? Now it's a flat, but the same idea will apply, right? The question is, I know this is the question asks you between 1 to 3, right? But what I have is what is less than 3, I know. Less than 1, I also know, right? Okay. Less than 1, actually 0, right? Because it's uniform between 1 to 4, right? There's nothing there. And less than 3, I know is F of 3. Just put in the formula, then we are done. Okay. So there are 2 ways to do it, but don't worry. This is the way we do this is we will repeat many times in our class. Okay. Look in the area, do the subtraction is something that we often do, and we will do it for the rest of the example as well. So don't worry if you don't do this. And only thing I have to emphasize is here, when we have continuous, less than or equal to has no difference. So this is why this is when we're continuous, the rainfall exactly 1 will be 0. So we can ignore it. Okay. It's what we call the measure 0 thing, if you technically. So same if I want between 2 and 3. Okay, that's how we do, right? We just 3 minus 2, right? Between 2 and 3 is probably less than 3 minus probably less than 2. All right, just to make it more implicit, right? Implicit, right? You want to calculate this, right? What you do is a high school math, right? Less than 3, right? You can calculate this area red, and you can look at which is give you coming from F of 3, right? Big F of 3, right? The area less than that, right? And also you can do the same. Area less than 2. Sorry, I should do this. Right? This area is F of 2, right? And you subtract the blue from the red, right? You get the purple, which is what you want. The pink, right? So that's how we get, we want to get the pink area. How we get that? The red area comes from the big F of 3. The blue area is F of 2. You subtract, you get the purple. Is that clear? And the F depends on scenario. And for the uniform, right? It's just very simple. F of x is simply x minus a over b minus a, right? A is the minimum, b is the maximum. So you can just apply this formula, and this is how it's done. Okay? I mean, of course, this is, if you learn it for the first time, this is a little bit tricky. But I hope you're getting more clear and clear, because we keep doing the same thing again. I mean, I'm sorry if you learn stat in the high school. This is something you do often, but we do it often, so don't worry about that. It's definitely not easy, but I hope at least you get the idea. With the assignment, then we know better. I mean, I often end a lot, like the math and stat. It's like swimming, right? I taught you on the ground how to swim. You may see, you understand or not. And no matter what, you have to go to the water and try out yourself. And you can try out your assignment, right? If you have time, or you can try out the exercise. I put it on the lecture notes, right? Not the lecture slide, but lecture notes. There has a lot of multiple choices. You can check it out with answers. Okay, so and there are no shortcut to math, right? You have to actually work on it. Remember how much math you do when you are in high school and primary school. How many addition you do understand addition. How many times you remember the times table. It takes a long time. Okay, so it's not that easy. So I'm not going to over the, for QFN student, please read them. Okay. So exponential, okay, as I mentioned, exponential is very simple. It's just like the Poisson, but instead of asking how many people come in, we are saying how long we need to wait a guy to come in. Okay, let me repeat the statement, right? Remember the Poisson application. Poisson application is asking the following, right? We have a timeline, say 1 hour, suppose, right? And lambda is 5, right? Means on average, 5 people come in. It can be 4, can be 3, can be 1, but on average it's 5, right? And we cut this into very small interval, right? And each interval, right, is following a binomial idea, right? But anyway, suppose this is a one guy comes in here and here, whatever. Suppose there's only 3 times comes in. The question is, how long you need to wait for this guy? Okay. And maybe how long you need to wait between 2 guys? Okay. All right. The last one is not there. Okay. So how long you need to wait to see the first guy? Right? How long is the next one? So on and so forth, right? And this, the time you observe the one guy come in can be modeled as exponential. Okay. So that means that as long as the total waiting time, that is exponential. Okay. And do notice the assumption behind the waiting time here. For Poisson, actually follow binomial, which means that every second, every different second, every minute is independent. Okay. So that's why I write in the lecture notes what we call memoryless property. Okay. It simply means no matter how long I wait, okay, and the time that for the next guy to come the same. Okay, what does that mean? It means that now I expect I need to wait 3 minutes for the first guy to come. Okay, now suppose I wait 1 minute, no one come. When next guy will come? Again 3 minutes. My answer will never change, even though the time had passed. Okay, that's no memory. Okay, if you not have, it's just like it's different from real world, right? If you think you are going to make an appointment with your friend for a dinner, you make meet at Mongkok at 8, right? If you're thinking how was the waiting time for him or her to come, right? If you wait the first minute, right? Probably you would think, okay, maybe he'll come in the next 5 minutes. After 5 minutes, maybe another 5 minutes, another 5 minutes, right? If you think no matter how long you wait, remain the same, then it's exponential. But if you think the longer you wait, it's more likely to come, then exponential is not the right one. But then you need to use more one, okay? But exponential, okay, has that property, okay? Whether it fit your case or not depends, but that is the thing that usually people use for the modeling, okay? Of course, you don't need to know the math, but you need to know what's the outcome. This is F, this is the big F. Usually, as I said, you only need to know the big F, okay? The small f is not important because we are not really doing anything there, okay? The big F is just asking how likely that you would come depend on minus lambda, right? And the E is the number 2.713, okay? And this is the time you need to wait, okay? And for many of you, you think this formula is not really friendly. Yeah, it's not very friendly, but just a formula there. Just this is we apply to that, okay? You never ask how your app in your iPhone or smartphone will work. Click, and this is the result, right? The black box, okay? And we're not going to open the black box because for QFN student, you have to know how to do it, but for rest of the people, we don't need to worry about it, okay? And actually, you can prove it. I think I'm not sure if I include in the proof. Yeah, I put in the proof. I don't, but if you look at the stat book, they will do the proof. I'm not sure whether the lecture look I do the proof, but that is the formula. Okay, the big F is important because that is what we do. Okay, but of course, do remember in the real world, you just use computer, right? Computer Excel will give you the answer. So even this formula is not needed. But we will probably, if you are asked to do for assignment, probably still need to understand this formula, how you get the numbers, right? So what is important is usually this guy, the mean and variance, beside the probability, okay? And it will not be surprising to you the mean is actually 1 over lambda. Why? Very simple idea. Consider the example we have before, okay? If we expect lambda is 2, say, for example, lambda is 2. On average, 2 people come in 1 hour. So you should expect 2 people come in. The most natural to think is you have 1 guy come in the middle, 1 guy come at the end, right? So this is very natural. Then how long it take for the first guy to come? 30 minutes, 1.5 hours, 1 over 2, right? So is that clear? So that is how you, of course, QFN student, you do the proof, okay? And variance, the same idea, okay? But the variance will be 1 over lambda square, okay? So this is something we need. So look at the example, okay? Remember the example here is the application is how long you wait for something to happen, okay? As long as you think, no matter how long you wait, the thing remains the same, okay? Oh, I do remember an example that's a good idea why the Poisson, right? I think you often go to a tourist site. There's always happen there's a mountain and there's a stone, okay? A human-shaped stone, okay? And this usually is, there's a sea over here, right? There's a sea, there's a hill here, and there's a stone, right? And often there's a story that there's a wife or husband or wife waiting for his husband to come back, right? 望夫石, something like that, right? Waiting for husband, waiting stone, right? The ship to come out, right? And you ask why he keep waiting, right? And then one day she become a stone, right? And then people ask why she's waiting, right? And she often said, he will come tomorrow, he will come tomorrow, he'll come tomorrow. And it's exponential, right? Because he's thinking, keep thinking, tomorrow he's coming back, tomorrow is coming back, tomorrow's coming back. So no matter how long he waits, he's being like this, right? So this is exponential. I think this is a good idea to explain what is exponential. And yeah, okay. So what is the time that you think is exponential? And mean is 20 minutes. Okay. And mean is 20 minutes. Okay. So, and that means 1 over lambda is 20. Okay. Remember, the mean is 1 over lambda. Okay. And you find out a lambda, and the question asking you how likely that someone come in next 10 minutes. Okay. So this is just this guy, right? Which is f of 10. And once you know lambda, you know everything, right? The only difficulty in this one is try to associate lambda with the mean, right? Because the mean is 20, actually means lambda is 1 over 20. The only difficult part is this one. Okay. If I tell you lambda, the answer is even straightforward. Okay. Is that clear? There's nothing deep there in this example. And this is something usually we care, right? And if we follow Poisson from 20 minutes, then when there will be 5 to 15 minutes that someone will come in, right? Again, 5 to 15, you take less than 15 minus 5. This is standard thing we use, okay? And this is the formula we apply, okay? And of course, as I said, Excel will handle this directly, but I just show you how, in principle, you're going to do it, right? Because Excel will immediately give you these two answers, okay? Two number without using that. We need to do that because you need to know how it comes about, all right? In principle. Okay. Is that clear what we're doing? Don't worry. You do the assignment, then you know, because this is something that all we have shown the assignment. So in the example is all we want to know. Okay. And you don't need to worry about when to use what. If given from your assignment in a test, I'm not ask you give a scenario, use which probability. Okay. It's slightly beyond what we are doing. Okay, there are many examples you can imagine. Okay, so you want to model surface time, right? How much time that someone will come in to ask for warranty surface, right? How long it takes for equipment to fail? Inventory management, how long you wait in order to restock, right? And project management, right? And these are the looking at the time something will happen. Okay, you want to model time? The thing, this is the model. Okay. So example, a call center, right? Is it in general, it takes 5 minutes to finish one call, right? And you assume exponential, right? Lambda is 1 over 5. And you can answer the question, how long does it take to handle 10 minutes? Okay. Is that clear? That's how this is being used. It's model in time. Okay, as long as you have the mean, the data, assume exponential, you know the future. So as long as you think, as I said, manualist, right? Like the woman in the stone, right? You think this is the way to go, then exponential is all you need. Okay. Another example is like the equipment failure, right? You want to model how long does it take for equipment to fail, right? And you think it's exponential, then you can just do the same idea. Okay. And here there's a slightly little bit twist. Okay. I use complement rule here. Okay. Maybe I should be a little bit more careful here. This one. Okay. this one is the complement of this 1 minus probability that x less than or equal to t, right? And remember, this is in fact 1 minus e to the lambda t. So 1 minus 1, so that's what you get. So I should be a little bit more slower, but I hope this is clear what's going on. Is that okay? So that's where the complement rule, right? You want to know how long does it take without things happen, and you probably want to know what is the average failure, how long it takes before things fails, right? And actually, that's why how the company give warranty, right? Usually you have one. Sometimes the product have 1 year warranty, 2 year warranty, 3 year warranty, and more, right? Actually, you calculate the cost of doing so is coming from this exponential, right? If you expect this is the right model and this is the, you can calculate how costly different warranty policy from a seller, right? So there's many things you can do. Is that clear? Let me further give more example. Say inventory management. Okay, also this is very interesting because time. Okay, suppose each time a customer arrives 10 minutes. Okay, every 10 minutes there's someone to come in on average. Okay, and you think you can model exponential, which means lambda is 1 over 10, right? And the question would be, you want to calculate how many stock you have, right? Suppose one guy come in and say, you're doing noodle shop, right? You are thinking how much noodle you want to get, right? You want to keep the noodle, right? And you want to keep, say, keep level of the noodle is 1 hour demand, right? Because the noodle shop may be very small, right? Maybe you're thinking about you're doing a store near the Promenade, Happy Hong Kong, right? There's a store in near the seaside, right? And you need to prepare how many sell mai, right? There, right? And you make sure that your stock is enough for 1 hour, right? Because you have to go to somewhere to grab the sell mai or noodle to your store. Your store cannot have many things, right? And you see how many you have to contain, right? And on average, you have to keep 6, right? Because 10 minutes, right? So it's the ideal Poisson, right? On average, you have 10 minutes, one guy times 6. That's how we do it. Okay, there's a standard way. That's how you Poisson exponential connect to each other, right? If you know this, right, you can go back to Poisson idea, right? Because it's a Poisson, right? Lambda is, so this is the idea, okay? And lastly, the project management, very quick, right? If you receive bug at the rate of 2 per day, then you can ask how you estimate how long it takes for bug to come in, right? It's half each day, right? You have 2 bugs per day, and then each half day you have a bug, right? Then you can see how to do the management more accurately. Okay, I hope these give you idea how you can use the probability modeling. So I will see you. There's no more I want to say today. See you next week. Stay safe. There's a typhoon might be coming with some probability. So I don't know. It's uniform, right? I guess it's not uniform. Binomial, I don't know. Whatever. See you next week on Wednesday.